All right. So what I'd like you to do, it might be a little easier said than done, is tackle the problems on the next page, and we'll start with those next class. You might find this surprising, but the easiest one to do on this page is number 3. Because you already know how to do it. All right? In number 3, it's already converted into spherical coordinates, and all you're doing is applying the multiple integration approach. All right? These other ones, we're actually doing the work to try to convert it over into rectangular form and seeing what it actually ends up being. All right, so that's where we're going to leave it for now. Question. Plot the point with spherical coordinates 8, pi over 3, pi over 6, and express its location in both rectangular and cylindrical coordinates. So really all it's asking us to do is identify the appropriate components and just plug it into some formulas. So, all right. So we could use our rules. We have some rules here that allow us to go right into rectangular form. So x is equal to rho sine phi cosine theta. It's going to be 8 sine of pi over 6 cosine pi over 3, which is going to be 8 times 1/2 times half again. So 8 divided by 4 is going to be equal to 2. All right, so we have the x value. The y value, rho sine phi cosine, no, sine phi, sorry, sine phi sine theta. So 8 sine pi over 6 times the sine of pi over 3. So a lot of consistency here. 8 times 1/2 times radical 3 over 2. So basically the previous answer times radical 3, so 2 radical 3. And then the z value is just rho cosine phi. So 8 cosine pi over 6 is going to be 8 times radical 3 over 2, which is going to be 4 radical 3. So therefore, in XYZ form, we're looking at 2 radical 3, 4 radical 3. All right, so that part's easy enough. Going the other way, it could be a little trickier. All right, but really, it's a matter of just using your knowledge of trigonometry. So, it's really not that bad. It just, there's a lot more moving parts involved. All right. When it comes to cylindrical form, well, we already got it in rectangular form. So if I want to go to cylindrical form from here, I would just need my cylindrical rules. So the z value is going to stay put. So I need, for cylindrical, I need r, theta, and z. So r is equal to the square root of x squared plus y squared. Theta, this is all from unit 1, so this is not new information. Inverse tangent of y over x. And z is z. All right, so I'm going to take my x value, square it. I'm going to get a 4. I'm going to take my y value, square it. I'm going to get a 12. the root of that, the principal root of that, square root of 16 is 4. All right, inverse tangent of y over x. So my y value is 2 radical 3. My x value is just a 2. Divide those two values. So 2 radical 3 divided by 2. We'll figure that out in a second. And my z value is 4 rad 3. '86 if you're looking. So the 2's cancel away. And what I'm looking for is the acute angle that has a tangent ratio of radical 3. That's why we've been doing that unit circle stuff this whole semester. All right, so working out from the x-axis, talking 1 over radical 3, 1, and then radical 3. So that's the 60-degree reference angle, or in this case, if we're going radians, we're going to say pi over 3. All right, now that was an unnecessary step, that middle one, but it was worth doing it the one time just to really show you, because theta is theta, right? I mean, there's a reason why we're using theta multiple times. If it meant something different, I would call it something different, right? I'd use a different representative for that angle. But what we're talking about in both cases, whether it's spherical or cylindrical, you're talking about the angle coming off of the x-axis going in a counterclockwise fashion around the xy plane. So you're talking about the unit circle, right? An angle in the unit circle. So why would the theta be any different? So going from spherical to cylindrical, really that middle component, not the problem. It's the other stuff that you need to figure out. And it really comes down to essentially the z value, because that's the weird one. Because the x value is pretty simple. I'm sorry, the z value is pretty simple. The x value is the weird one. So surfaces. In A, we have rho equals 13. So rho is going to be equal to the square root of x squared plus y squared plus z squared. But this says rho squared, so all right, I'll go the other way. Instead of saying rho equals 13, how about I say rho squared is equal to 169? So then I could do a clean substitution, replacing the rho squared with the x squared plus y squared plus z squared. That is not a highlighter. That's a highlighter. All right, so you might not have recognized it in the original form of rho equals 13, but the fact of the matter is, once you convert it into rectangular form, it's pretty clear that that is the equation of a sphere with center at 0, 0, 0 and radius equal to 13. Right, so then it kind of begs the question, well, why would I ever convert it over into rectangular form if it's so simple in spherical form? It's just a constant value, rho equals 13, that's it. Right, really, if you think about it, all you would need to do, if you're talking about a sphere centered at the origin, all you'd have to do to define that sphere would be to just talk about an expression that represents how far it's going away from its center. And since it's always going to be 13 units, no matter what the direction is, rho equals 13 gets the job done. You know, just like r equals 13 would get the job done in two-dimensional space. Right? If you're talking about just a circle in polar form, r equals 13, that's perfect, radius of 13. And in fact, if you were to decompose this down into the two-dimensional plane, to slice it right along the XY axis, that's what you would get. You would get the circle whose equation is r equals 13. Next up, a little bit of a different story, because in this case, now it's saying that an angle is constant, right? Now this is the angle around, or the angle living in the XY plane, but it's talking about for all values of rho and for all values of phi. Right? So what we would need is some sort of conversion, the ability to convert from this form into spherical form, right? So, you could do it by coordinates, but you'd have to somehow account for the fact that the rho value and the phi values would be variable, right? So that means it's going to go potentially all the way around, starting at the z-axis, all the way around, right? Living on one particular theta value. So that would in and of itself make a circle, right? But then if you're allowing for the fact that rho could be anything, then you're giving it infinite dimension. All right, so it's kind of weird to think that this is somehow going to end up being the equation of a plane, but that's exactly what it is. All right, now, when you think about it, in two-dimensional space, theta represented the equation of a line. So if theta was a constant value, it ended up being a line. If you expand it into three-dimensional space, you're adding another dimension, so maybe that would be the case, But maybe, so that's what I'm going to do. For B, I have theta. I'm going to leave a little space here is equal to 2 pi over 3. I'm going to take the tangent of both sides. As long as you know what the tangent of 2 pi over 3 is, you should be in pretty good shape. All right, so tangent of theta is equal to, so you're taking 3 steps up in the second quadrant. Second quadrant makes tangent negative. All right, but the ratio is going to be the same as 3 steps up in the first quadrant, so it's still going to be radical 3. All right, now tangent itself is the same as y over x. So y over x equals negative radical 3, which means that y would be equal to negative radical 3x. Now you might say, well, that's not a plane. I say, but wait a minute, we're in 3 space. We're in 3 dimensions. There's no mentioning of z, so it implies that this must be for all z. All right? So it's kind of strange to think of it that way, but that's how it works. And the visual aspect of it is pretty crazy because you're kind of relying on me to do the hand waving. That's dangerous because GeoGebra, maybe it's me. If it handles spherical coordinates, I haven't figured it out yet. It can do some stuff with cylindrical coordinates, but I haven't figured out how to handle it with spherical coordinates. But basically, this is saying, so you're just kind of working around, like the equator, starting at 0, settling in at 2 pi over 3. So that would give you a line in 2 space. But then I'm saying that, so we're accounting for the fact that phi could be anything, which allows you a vertical circle. All right, so I'm at a circle now, depending on what phi is. So on this line, which would represent my diameter, I can be a circle. All right, but then what it's also saying is that since rho could be anything, that circle could have infinite diameter. So it could go out that away forever, that away forever, that away, and so on, as far as you can imagine. So yeah, it's going to end up being a plane, assuming that the outer boundaries of the universe is rectangular, and that's how we define a plane. But the reality is, we don't know what anything looks like out at infinity. So as long as it gets to infinity in every direction, it satisfies the definition of a plane. So that's kind of a weird thing to think about, that somehow a circle becomes a square. Like that, it sounds like a game show, but it's not really anything more than that. Now for C, phi is settled in on a particular value. So if you're thinking of phi as, so you have your z-axis, phi represents an angular movement off of that z-axis. So that's going to be fixed. All right, so in two-dimensional space, you know, if you have a vertical plane, that would still be a line. But now I'm saying that it's for all theta. So that means it's going to spin around. So now it's a cone. All right? And then it's going to shoot up in as far as you can go because it's for all values of rho. So the radius could be infinite. So you've settled in on a phi value, so that's your angle from the z-axis, but you're allowing theta to be infinite, which means you're allowed to spin it around. So the elbow is where you're pinning that line segment, which goes on infinitely. So visually that would have to be a cone. All right, so our job would be to figure out what the equation is of that cone. All right, so anyway. Just to actually answer the question. I tend to get a little excited about this stuff. So it's phi equals phi is equal to pi over 4. I'll hang on to that for a second. We know that cosine of phi, just force of habit, is equal to the square root, z over the square root of x squared plus y squared plus z squared. Since I want to get it in rectangular form, I could use the arc cosine rule, the inverse cosine rule. I don't want to. The reason I don't want to is because if I do that, I'm going to get something in terms of phi, which I'm just going to find the cosine of anyway. So I'm going to find the cosine of this phi. Let me highlight. Cosine of that phi is equal to root 2 over 2. All right, now that's a perfectly acceptable way of representing your rectangular form. Problem is, it doesn't tell us much about the structure of things. So maybe we want to clean it up a little bit. And I would do that by squaring both sides. Now, somewhere along the lines here, hopefully you're thinking to yourself, thank God I really practiced my unit circle trig throughout the semester. Because there's always a good segment of the population who feel that way. It's like, okay, I know where the rad 2 over 2 came from. All right? But then there's also the other portion of the population that's like, I really wish I studied my unit circle trig stuff over the course of the semester. I mean, it ain't over yet. This next test is open notes, so like, is it really that big of a deal if you don't have, instant knowledge of the unit circle? No, because just bring an old unit circle quiz with you, and then you'll have instant knowledge, I guess, So all that stuff is fair game. Old tests, old, notes, anything you could think of. As long as it's not digital, you're good to go. All right. So, say it again? No, finals, we're going with different rules for the final. Final, we're back to an index card.
Index card, no sheet?
No, just an index card, yeah.
You said that you had 3 tests as part of the final?
Yeah, I mean, if you didn't have open notes, hell yeah. But with open notes, it should be at least on par. So I square both sides. I'm going to cross multiply. I'm going to get 2z squared is equal to x squared plus y squared plus z squared. Can combine some terms, bring the z squared over. So z squared is equal to x squared plus y squared. Take the root of both sides to get z equals. And you get z equals the square root of x squared plus y squared. So that's actually the equation of a cone. But not because I'm looking at that equation and saying clearly that's the equation of a cone. It's more so because I'm just going back to the visual that I determined based off of the value of phi and knowing what rho, theta, and phi all represent. That's what gets me to the point where I understand that this is a cone, not this equation. I mean, I suppose you could just start plugging in points for x and y and see what that gives you in terms of z. I mean, that would pretty much take you the rest of your natural life to do, but you know, like you can get there. You could also look at it like in the previous form, you have x squared plus y squared equals z squared. That's kind of like x squared plus y squared equals r squared, which is the equation of a circle, right? So with the center at the origin. So if z is equal to 0, you have a circle radius of 0, so a point. If z is equal to 1, you have a radius of 1, circle radius of 1 at a z value of 1. So you'll have an elevated ring, right? That's 1 unit above the xy plane. If z was equal to 2, you'd have a radius of 4, so an even bigger circle, Eventually you get to the idea that that's going to represent a cone, but only if you have that linear aspect to it, right? Because you know the trace of it happens to be linear if you slice it right down the middle, right? So that could be tricky, but you got to be able to recognize this in some way, and that's part of the fun. Now, number 3 I mentioned as something that even though it's in cylindrical form, it's something you could easily handle, and that wasn't a lie. It's because you didn't have to convert anything into, I think I might have said cylindrical, I meant spherical. It's in spherical form, but it's still a triple integral. We didn't have to actually convert it to spherical form. It was already in spherical form. The challenge in this stuff is never going to be to actually integrate it. It's going to be to get it into the appropriate form in order to integrate. All right? So on the test, you're going to see some of the problems are just going to say, write an integral or a set of integrals that could be used to find the volume in spherical coordinates, in cylindrical coordinates, whatever it is. Because for that, I'm just looking for the setup. I don't even care about what the answer is. Right? Because honestly, once you realize, for example, in 2C, that it's a cone, part of you should be thinking to yourself, well, couldn't I just use the volume of a cone formula? You know, that's not unreasonable. You know? So I want you to demonstrate the ability to use a triple integral to get to that value. Or actually, I mean, if you want to get creative, use anything that you can think of as long as it involves an integral, right? And the appropriate coordinate system. So evaluating this triple integral, again, super easy, barely an inconvenience. Just integrating with respect to rho. So 1/3 rho cubed sine of phi on the interval of 0 to 1. All right, plug in a 1. You're going to get a 1/3 sine of phi. All right, plug in a 0, it's going to zap away, so that part's taken care of. All right, there's no theta in here. So the second part of this process is not going to have anything to do with multiple integration, or at least the concept of partial integration. It's going to have to do with just the ability to integrate in general. And that could be on your calculator, but again, once you get into circular functions, sometimes you want to do at least some of it by hand because, you know, pi being a thing, you want a clean answer. Not that I'm requiring that, but if you want a clean answer, that's how you're going to get it most of the time. Unless you're pretty savvy with the calculator, as we've been talking about. So 1/3 sine of phi d phi is going to be, or the integral of that is going to be negative 1/3 cosine of phi on the interval of 0 to pi over 2. All right, so we're looking at, Well, the first part's going to zero out because cosine of pi over 2 is 0. Minus negative 1/3 cosine of 0. My pen turned off. Two negatives are going to give me that positive. Cosine of 0 is equal to 1. So 1/3 times 1 is 1/3. All right, so now I'm in the grand finale here on the interval of 0 to 2 pi, integrating just the 1/3 in d theta. You're going to get theta over 3 over the interval of 0 to 2 pi, which is just going to give you 2 pi over 3. All right, now I suppose I could try to motivate you by converting this over into rectangular form, just to show you how nasty this would be if it were a rectangular function, x, y's, and z's. Because you not only would have to convert over the function itself, you'd have to convert over the d rho, d phi, d thetas, and all the bounds. Right? So it's really not worth it, because I think just based off of the fact that it would have taken us longer to type this into our calculators than it did to actually figure it out by hand. I think we're sold on the idea that this is a good way to do it when it's appropriate. Right? So then the big question becomes, well, how do you know when it's appropriate? Well, circular functions. That's the name of it. Right? If one of your equations is a sphere, well, spherical coordinate, that's the obvious thing. But anything that's circular in nature, almost in nation, is going to lend itself to spherical coordinates or cylindrical coordinates. All right, so really it's going to come down to your knowledge of whatever z is. All right, so if you have some known bounds for z, then maybe cylindrical coordinates. But if not, then spherical coordinates would be the way to go. All right, so it's going to come down to converting over, and then doing some pretty easy calculus. Now, if you had something that's not circular in nature and you wanted to go to spherical coordinates, that's when you could end up paying a price, right? So you don't want to just say, well, I'll just do everything in spherical coordinates. Why didn't we just start doing this in Calc 1? Because if it's a rectangular function, then rectangular form is appropriate. So something that's got angles to it, so linear, absolute value functions, piecewise functions, things like that, they're going to lend themselves to rectangular function form, right? But if it's circular in nature, basically anything that's got a significant curve to it, right? So thinking back to the last unit when we talked about curvature, it's got significant curvature to it, then spherical coordinates is most likely the way to go. I won't say it's a waste, but it's not as thrilling. This one, if I give you a diagram, things get a lot easier. You could expect a diagram on a test, because the hand waving part, that's, like I said, I mean, when I'm making my gestures and spinning around doing pirouettes in front of the class, it all seems to make sense to me. That doesn't mean it's going to make sense to anyone else. All right, so for these kind of questions, I always give you a diagram, and when that happens, things tend to get a little easier. All right, so set up an integral for the volume of the region bounded by the cone and the sphere. All right, so it's bounded by the cone and the sphere. So it's not the area, the volume below the cone. That's different, right? When you're talking about cylindrical coordinates and rectangular coordinates, those integrals, they give you the volume between the function and the xy plane. The spherical coordinate integration does not do that. What it gives you is the volume contained within the function, right, as it surrounds the z-axis. Right, so your point of reference is the z-axis, not the xy plane. Right, so it's a change in the way we're thinking. However, that's going to benefit us here, because it just so happens, if we're talking about bounded by the cone and the sphere, we're talking about basically this ice cream cone in the middle. Right, you got the cone here, and then you got the little ice cream on the top, perfectly spherical in shape. But we want all this crap out of here. We don't want that to be included. Right? So if you think about how that would work in rectangular form, you would actually have to figure out what the volume is of the hemisphere and then figure out the volume underneath the cone and subtract that off. Not to say that that's overwhelmingly difficult, it's just not as easy as working with it in spherical coordinates. Right? So what I need is the difference between these two functions, or at least functions that represent that. All right? So
Getting the volume without the cone.
the
Hemisphere, half hemisphere.
volume in the half hemisphere, in the hemisphere within the cone. So the cone is staying there. It's everything outside the cone we're excluding. That's not going to be there now. Whereas if we did it with cylindrical coordinates, we would only get the stuff outside of the cone. Right? So just to kind of highlight it, it's going to be, cannot draw, as we all know. We got here, we got here, we got here, and I want all of this stuff. And my diagram just went to hell. It had promise early on, now I'm just scribbling. But basically, I want all of it, everything in here. All right, but everything on the outside is gone. I don't want any of that. All right. Now, fortunately, we have equations that represent those two important components, the cone and the hemisphere. All right. But we don't want to lose sight of the fact that even though it's written in z equals form, when I square both sides, it becomes z squared. We still only want the top half. All right. So I'll start with, I'm not even going to bother color coding it. It's just going to be a disaster. Z equals the square root of 3 times x squared plus y squared. Square both sides. Poor quality x squared. All right, so we have this. I mean, it's something, but I need it to be something more. All right, it's not gonna cut it in this form. All right, we know it's related to a cone, but that cone has a multiplier associated with it, so we have to account for that. Let's get everything over to the same side. So 3x squared plus 3y squared minus z squared equals 0. All right. Well, actually, check that. Let's not distribute the 3. I'll just write it as a next step, basically undoing what I just did, but if you want to erase, that's fine. Because I could just do a quick substitution here, because we have this guy. 3 rho sine of phi minus z squared is equal to 0. And z is equal to rho cosine of phi. So, quick substitution here. We're going to have 3 rho sine phi minus rho squared cosine squared of phi equals 0. All right, because it's z squared, so we got to take care of that. Now, you'll see in a sec, it's going to be pretty annoying when this all comes out in the wash. But sometimes you just have to go through the growing pains in order to understand why. So you have a common row, 3 sine phi minus rho cosine squared phi equals 0. quadratic in nature, so I can solve rho equals 0, 3 sine phi minus rho cosine squared phi is equal to 0. The second equation we're not going to be able to do anything with. You have one equation with two variables. So, toss. After all of that, you got rho equals 0, which should be pretty annoying, but maybe it's not a big deal. All right. Yeah, it's basically because that's a cone, right? It has the same structure. Z is equal to the square root of x squared plus y squared, except it has a coefficient of 3. So if that's the case, that's fine. And that's telling us that it's still going to be a cone no matter what the coefficient is of x squared plus y squared. Right? So if that decomposed down to 0 for a cone where there was no coefficient, then it shouldn't be shocking that it goes down to 0 when the cone has a coefficient other than 1. All right. The other equation, z equals the square root of 4 minus x squared minus y squared. Square both sides. This one's a lot nicer because you have x squared plus y squared plus z squared equals 4, which means rho squared is equal to 4, which means rho is equal to 2. All right, so here's the deal. You could have figured all this out without doing any of that work, just by looking at the picture. All right, because you'd want to be thinking, all right, is this whole thing symmetric about the origin? Yeah. All right, it's centered at the origin, and you're going equal distance in each direction. All right. Talking about a hemisphere, which means that the distance outward to the edge of that hemisphere is constant. All right. Regardless of what it's constant at, it's going to be a defined value. They happen to tell you a coordinate at the outermost part of that hemisphere, having a z value of 2, which means that up the z-axis, the furthest you can go is 2. If it's constant radius, it's got to be 2 everywhere, right? So I would know that if I'm spanning out in terms of radii, I can only go from 0 to 2. All right, so make use of the picture. So you have your rho, all right? If you know what theta represents, then you already know that theta is going from 0 to 2 pi, all right? We're not even at the part where we're writing the multiple integral yet, all right? Here's where the x-axis lives. As you go around the unit circle in the counterclockwise direction, you start at 0, and then when you come around the other side, you cover 2 pi in terms of radians. All right, so we know what the values are in terms of theta. All right, because it's just a unit circle. It's just how far around are you going. Now, if I only did half of the hemisphere, then I would go 0 to pi. Quarter of the hemisphere, 0 to pi over 2. All right. Now, in terms of the phi value, I would want to be thinking, all right, where does my bounded region start and where does it stop? Hint, it always starts on the z-axis. All right, so my phi value is going to start here at 0, so phi equals 0. Now, since the volume that I'm interested in is the cone itself, not everything but the cone. It's that purple shaded region. I want to expand out my angle phi until I've covered that entire region. So I don't want to go all the way down to the XY plane. I want to stop right here. All right, because that's what this angle is going to be here. That's my phi. All right. So that's that stupid pirouette I did before. I start at the z-axis. I'm going out some phi value. I'm covering the space in between the z-axis and wherever my outer phi is, but then I'm covering 2 pi radians. So that's going to spin me around the whole way. Kind of like volumes of revolution from Calc 2. All right. So if I figure out what that bad boy is right there, then I'm going to be in good shape. All right. So what that means is I got to figure out what that bad boy is in order to be in good shape. So that's what we're going to do. What that essentially amounts to is just setting these two things equal to one another. So the square root of 3 times x squared plus y squared and the square root of 4 minus x squared minus y squared. Square both sides. Easy enough. All right. I squared both sides. Yep. So we can factor out a -1 here. So 4 minus x squared plus y squared. Now, ultimately, we want a phi, so I want a rule that involves a phi. Well, I have a rule that involves a phi. A couple pages ago, I believe I starred this one and said it was really important. You're starting to see why, hopefully. So 3 rho sine phi equals 4 minus rho sine phi. Combine. Oh, and it's up to you, but at some point we're going to plug in the rho value. You can do it now or you can do it later. I'm going to do the algebra though. So 3 rho sine phi plus rho sine phi equals 4. Combining like terms, 4 rho sine phi equals 4.
Isn't the rho sine phi equal to radical x squared plus y squared?
Krispy Kreme donuts. How did I flub that up? Inquiring minds want to know. Nothing to see here, nothing to see here. Thank you. So an extension on this, rho squared sine squared phi would be equal to x squared plus y squared, allowing us to make that nifty substitution. Otherwise, all goes to hell very quickly, as I effectively demonstrated moments ago. All right, so kill the 4's. Rho squared sine squared phi is equal to 1. All right. Now, if you're living on that outer portion of the sphere, rho has to be equal to 2. All right, so if I'm looking for that point out there at the outermost component, or outermost bound of that region, then rho would have to be equal to 2. So I can replace rho with a 2. So 2 squared sine squared phi is equal to 1. So it's sine squared phi is equal to 1/4, making sine of phi equal to 1/2, and at long last we get phi equal, if I can properly make a phi that doesn't look like a y. Try that again. At long last, the phi equals pi over 6. All right. So, because the sine of 30 degrees is 1/2. So a little work here, but it's the trade-off because really all this other work was really unnecessary. So this is the only work that was necessary. Now, if you're running under the assumption that we're working with clean values for our angles, I mean, you got 3 possibilities. If you're going to take a guess, it's going to be one of 3 possibilities. It's going to be pi over 6, pi over 4, pi over 3. All right. So worst case scenario, you just flat out guess and go with it. The better case would be to actually plug, take your phi equals pi over 6 and convert that into rectangular form and see if that's consistent with your cone equation. All right. So that would be the better way to handle it, but we all do different things, especially when we're panicking. All right, so we did a lot of work there to not have the answer yet, but the answer is we already have it. All right, so that was all the work, because now my triple integral, because I only have to set it up. Rho squared. So that really amounts to everything. So rho squared sine of phi d whatever, it doesn't really matter. All right, d rho, d phi, d theta. It makes sense to put it in that order because your function itself has a rho and it has a phi in it, so you'd want to take care of that before you even get started. All right, so from our diagram, we knew we were going from 0 to 2 pi. From also the diagram, we knew that we were going from 0 out to 2. And then from this work here, my color coding got screwed up. From this work over here, we knew that we were going from 0 to pi over 6. All right. So that triple integral will give you the volume contained between the cone and the sphere.